What? No.
Alright, so move these airplanes. Alright.
Hold on, I got this.
Oh good, we have another black pen.
Turn on
The
autopilot.
white ones don't work so well. Let's see which one works better. Alright, last time we were discussing some properties, we did slip systems, all that kind of stuff, resolve shear stress, and so on. Didn't quite get to hardness and creep, so I've talked already about hardness being a measure of an ability's resistance to deformation. And I think I talked about this, but I want to make sure. We basically take a steel ball or some other kind of known geometry, a tip of some known geometry. Yeah, it's supposed to be a ball. Anyway, and apply a load to indent the surface. And if the hardness of the tip, the only key is the hardness of the thing that you're indenting with has to be much greater than the hardness of the surface. Obviously, because we don't want the ball to deform. So the idea is to use a really hard steel ball for a soft aluminum surface, or if you've got a really hard surface, you use a diamond tip instead of a ball. So if you use the diamond tip, then it's going to be, some kind of a diamond indenter like this. Okay, that has a known geometry, so we know what the size of that thing is. So then when it's removed, there's a residual dent. So this is the first step. The second step is to then measure the dent, either to measure the width, well actually typically you measure the width. And from the width you can get the depth because you know the geometry. So you know how far it indented the thing. And then the third step is to apply an empirical formula. And according to this, it's on page, it says 182 here, I'm sure that's probably not the same page in the new edition of the text. So let's look somewhere around 200 and see if we can see that where that formula is. Hardness, so we're close. No, 184 now. So there's a formula actually on page 183 to determine the Brinell hardness number, and it depends on the load of you're pushing down with, the diameter of the sphere, and the diameter of the indent, little d. So big D is this, big D here. That's little d. That's big D in there. And this is load P in their nomenclature. But anyway, so you have a formula to determine out this empirical formula from which you can get hardness.
What's their nomenclature for the depth then, in the case on the left? Like the depth of the
They don't, we use one in the book. I don't think the book, that's what I was looking at, I don't think they've got a,
Okay.
they don't use a letter, to designate that. But the point is for a fixed, there's a fixed correlation between these two.
Yep.
Okay. And so they actually calculate the Brinell hardness number in terms of that depth, but they don't actually assign that value, that depth of value. Okay. And hardness then correlates to yield strength and ultimate tensile strength. Okay.
Do you have a radius of number one is capital D for the radius? Or is that
Yeah, sorry, that's supposed to be diameter.
Okay. Really just checking.
The yield point or the ultimate tensile strength. And again, you can measure for very hard materials, or for very like thin materials, you'll typically use something that's a very fine diamond tip and apply a very small load. Yes.
So is this mostly, does this only apply to like metals? Or can you do it with ceramics?
You
Like
can-
I'm trying to picture it being
yeah,
done
you-
with glass, I feel like.
You can do it with anything that will deform. You can do it with ceramics, though not all ceramics have enough plasticity to them. So there are some ceramics that have enough plasticity to be able to dent them this way, to do this. They're tough enough. There's some tough ceramics that you can do indentations with. So silicon nitride is one. You can measure the properties of silicon nitride by doing little Vickers indents. The problem is that it actually generates little cracks coming out the sides. So it's not really as non-destructive as you'd like it to be. But the idea here is if I've got a big, steel ship, and I want to somehow check the mechanical properties at various points in that steel ship, I can't cut out a sample and go put it in a tensile machine and pull it, right, to measure these. So instead, I go up with this little device and do the little indentations on it, and I can then measure locally in what is effectively non-destructive on the scale of the ship, the properties at local points. Now, the downside to that is I'm only measuring the surface. I'm not measuring what's inside. But it's particularly useful if you've done a weld on something, you've done a weld on an area and you want to see if in the process of welding you've changed the mechanical properties of the steel adjacent to that weld. So you can go in and kind of do these little indents along a radius away from the weld and see how you've altered the mechanical properties. Okay, so there's different ways in which we can do this, but it's essentially just a means of getting at mechanical properties without having to go through a tensile test. Okay. And there's a correlation then on page 184. There's a correlation between the yield strength and the tensile strength, the yield strength, the ultimate tensile strength, and the Brunel hardness number. And you can see there's some sort of, they're bands. They're not direct one-to-one correlations, but there's bands of correlation between those two. Okay. All right, that's hardness. And then the other thing that I didn't get to talk about last time was creep. This one actually has a little more foundation in the material science we've talked about. The creep is deformation that occurs under constant load and elevated temperatures over a long time. So it has constant load, elevated temperature, and long time. When those three things are present, this one's not any better than that other one. When those three things are present, and by elevated temperature, I mean temperature greater than somewhere between 0.3 and 0.5 of the melting temperature. So we're talking pretty high temperature. So if the melting temperature for, I'm trying to think, the melting temperature for aluminum is like, I don't know, what is it, 900 Kelvin? It's got to be in here someplace. Melting point, aluminum, no, 660 degrees C, so yeah, 930 Kelvin. Okay, so you'd have to measure this. This has got to be measured in Kelvin. So that means that you're anywhere from 0.3 to 0.5 of 930, which means you're somewhere between 300 and 500 Kelvin. Room temperature is 300 Kelvin. Okay, so for aluminum, we're not that far away from being able to observe this phenomenon.
If you get over the 0.5 of the melting temperature, it is no longer able to happen.
There's, if you get too hot, you essentially get softening of the material. You actually, there's too much, it's too, it's then you're going to do phase changes and stuff. So it's not, this is primarily, creep is something that primarily is thought of as occurring in sort of normal usage environment. So something where you use, in the temperature range where you would normally use the material. And if we plot the true strain, not the engineering strain, but the true strain as a function of time, I load something up and it's got a certain amount of strain on it. All right, so remember our stress strain curve looks something like this. Right, here and now I'm drawing it some reasonable facsimile of the actual behavior. So I pull this thing up to this point right here. And so I've caused some plastic deformation, but I've just deformed it, that's it. I pulled on it, I bent it, whatever, but then it's just, I'm holding it right there. Okay, the load doesn't change, constant load. What happens is that strain over time will do that. Right, so there's a certain amount of strain, actually I shouldn't draw it like that. Right, this is what I'm plotting right there. That amount of strain starts out at whatever it is, and then it increases over time in 3 different phases. 1, 2, and 3. Okay, in step 1, this primary stage of creep, what's happening is the vacancies are mobile because we've got a fairly high temperature. Right, we talked about vacancy mobility sometime when we talked about Arrhenius behavior. Right, the probability of having vacancies and their ability to move around is dependent on temperature through an Arrhenius behavior. So you have enough temperature, enough thermal energy to get the vacancies moving around and create a bunch of vacancies. So in this section you get dislocation climb, which means the dislocations that look like this. Right? If I keep filling in these atoms with vacancies, I can get that dislocation to move. You see what I'm saying? If I get vacancies to sort of control, and you can imagine the vacancies would want to be here because this is an area where you have compression. Right? The lattice is squeezed together up here, so I have compression on the top and tension on the bottom. So I'm kind of wanting to squeeze those atoms out anyway. There's already a force acting to kind of squish those atoms out. So if I've got vacancies, the vacancies are going to be attracted to this because vacancies have a tensile field around them. Right? All of the bonds are being stretched. You follow what I'm saying? If I pull an atom out, all the other ones are going to collapse and it's going to have a tensile field. Well, tensile and compressive are going to be attracted to one another. And so those vacancies are going to be attracted, mechanically attracted to this area and cause the dislocation to climb up. So I'm going to get deformation. I'm going to get change in the alignment of the lattice just because vacancies move around. Okay?
What are each of those sections?
3 different phases of creep. There's stage 1, stage 2, and stage 3 of creep. This is all just so stage 1 is where I have, in stage 1, this is the area where I have dislocation climb due to vacancy formation. In this section, it slows down because what happens is I create new vacancies, or new dislocations rather, that exactly balance the dislocation climb, or almost balance the dislocation climb. So the dislocations are able to move around. Okay. And then the third section, this is rapid increases caused by necking. So again, I'm plotting here true strain, not engineering strain. So eventually, as it begins to neck down, and the dislocations or the deformation starts to build up enough that it's necking, then the apparent strain takes off. Because now my cross-sectional area is much smaller, and so it elongates much quicker. Okay.
What exactly is creep, though?
Creep is an increase in strain over a function of time at elevated temperature. So in other words, I hang a mass on a wire, and it hangs right here. I come back later, it's hanging here. Come back next week, it's hanging here. It is, you see what I'm saying? The strain in the wire is increasing over time, even though the load is staying the same. You have the same mass hanging from the bottom. Yes.
That's basically what you have to worry about with buildings, and you have to make sure you keep up with checking on buildings, make sure they're not Like, is this
So-
something that can happen to a building?
It's not, it doesn't generally happen on large scales like that, it usually happens, I mean, because on a large scale like that, first of all, it's over-engineered, but second of all, you know, the melting temperature of steel, which is the main construction material, is way higher than we have to worry about here.
But like, I mean, if you like set something up and it's like, oh, it's working, and so then it just falls apart, this could be.
So it is possible, for things to fail, yeah, but generally it's gonna be something in a relatively high temperature environment, so it's not gonna be something happening at atmospheric temperature. It's probably something happening in an oven or something.
Okay.
But not an oven where you're melting it. You know, you're doing it in an oven where at the temperature when you did it, you know, the first time you did it, everything was hunky-dory. Right, so it sat there and it didn't deform. But then over time, the deformation increases because of all these things. Vacancies are moving around, dislocations are therefore able to propagate and cause deformation, yes.
Just like what kind of time scale?
Oh, it can be very long time, I mean, like hundreds of years time.
Okay.
It depends on the, you know, where we are and what temperature and what the load is.
Are you familiar with the pitch drop?
Right, so the pitch drop is an example, except that that's not really creep, because the pitch that's dropping is not, it's not a solid. Same thing's true in window glass.
Can you explain the pitch drop to us?
It would be something you'd have to, look it up, look up pitch drop on the internet. There's a,
Let's pitch with a P. Oh, just jokes.
Boo, bad joke.
so there's a blob of pitch, like really thick tar, you know? And I'm not sure where it is. Where is it, do you know?
It's somewhere Great Britain.
Yeah, I thought it was in England someplace. That is dripping, there you go. And it is dripping so incredibly slowly. They had a drop come off, I think, in the last year or two.
That's exciting.
That was, yeah, the first time it's happened, and it was just really slow. But anyway, but this is different. This viscosity, this creep is different than viscoelasticity, which is a different thing I'll talk about in a second. So creep is actually a metals thing primarily. Window glass does the same thing. Window glass is actually viscous. It is not, window glass is technically a fluid. Okay, the glass in the windows is a fluid. It is not a solid in the official sense, because over long periods of time it can flow. If you go to the, look at the windows of cathedrals in Europe, you know, they've been around for hundreds of years. The glass at the bottom is thicker than the glass at the top.
That's why you get that like Ripley effect.
So that's, the Ripley effect probably has more to do with the fact that the way they cast it, because they couldn't make it.
Does that make it like a non-Newtonian fluid?
Is it a non-Newtonian? I don't know if it's a non-Newtonian.
Because you know how when you have like that goop stuff, you can sit it and it
Yeah.
gets hard, like with this it'll shatter.
Yeah, I don't know if that really makes it a non-Newtonian fluid.
Not.
Anyway, okay, creep is a different thing. Creep is purely, actual deformation is occurring. Dislocations are propagating, the material is deforming, but it is not flow, which is what happens with pitch or glass, window glass, it's not flow. Okay. All right, and the other thing is, even in situations where we don't have, like if I take this thing and I stretch it and between two walls, right, so in such a way that it's not able to creep, I can get stress relaxation. So what will happen is, instead of moving horizontally on this graph, it'll move, vertically, it'll move down. So in other words, if I have a chunk of aluminum sandwiched between two platens, and I load it up and it's in there, and then I let it go and put it in an environment where creep can occur, it obviously isn't going to change its physical dimensions because it's bound by the two sides. But the stress within here can decrease. Okay, so there can be an erroneous behavior for the stress as well. No, yeah, it could be a bad thing. You know, it could be a good thing, depends on the nature. Everything, there's not much in here that we talk about that is universally good or bad. Everything we talk about in here is typically good or bad, can be used for good or bad, depending on the particular situation what we're talking about. Even glass cracking. right? You think, oh, you don't want your glass to shatter. There are times you want your glass to shatter.
And it's a granite, like with safety glass.
Right, exactly. So all these things can be used for good or evil. All right, so that's creep. Then viscoelastic deformation, the pitch kind of a thing, is a different deal. Okay, it looks a lot like it, but viscoelasticity. Viscoelasticity. This is primarily something we see in polymers, so pitch is a polymer. If I take on a log scale, I plot the elastic modulus of the material, the polymer, as a function of temperature. There are two distinct transition points. So we have a rigid polymer. And we take that rigid polymer and when warm it up and does something like this.
What's E?
Elastic modulus. The slope of the stress strain curve.
Yeah. And T is what?
Temperature. So at low temperatures it's rigid. But if I get up to what is called the, I have that down here, the glass transition temperature, T sub G. In ceramics it's glass transition temperature. I don't think it's called this, I don't think it's the same name in polymers. Anyway, I get up to a certain temperature and suddenly the stuff becomes soft. It doesn't melt, it just becomes soft. And so I would call this region here kind of leathery. Then we get down to this section down here, so that's the leathery region. Then we get down here, and this section is rubbery. And then down here, it's viscous. So what's happening here is in the central region, the temperature is high enough to overcome the secondary bonds that are holding the polymer chains together, but not high enough to overcome the primary bonds that form those chains. Okay, so I'm not sure how you guys feel about your chemistry, but you understand the difference between primary and secondary bonds? Okay. So if I have some kind of poly something lean, right? Polyethylene, poly whatever. Right? It's a bunch of carbons with hydrogens on the sides, and I don't generally draw the hydrogens. Okay. If I have another chain right next to it, right? Those two chains, there can be a secondary bond of connecting these two chains together. Between the hydrogens, right? Or if there's a chlorine, if it's like PVC or something, there's there some of the side bonds, the side atoms on the sides of the chain can interact and create secondary bonds. But they're not actual cross-linked bonds. They're not bonds where this is actually forming a permanent bond with the thing next to it. They're secondary bonds. They're van der Waals forces. Again, you guys haven't had that. What's that? Kind of like hydrogen bonding, right? So for anybody who's had enough chemistry or remembers enough chemistry, that's what happens. But they're very low energy bonds.
Is that what happens when we cast plastics or mold plastics?
So when you make, I'll use a rubber band as an example, right? When I make a rubber band, I've got a whole bunch of these long chains. And these long chains are all kind of coiled up in this chunk of rubber. Okay, they're all coiled up amongst each other.
Secondary bonded or primary bonded to each other?
They are secondarily bonded to each other, primary bonded to themselves. So there's this long chain of primary bonds. But the thing holding the two chains together is a secondary bond. okay? It's enough to hold it together so that it has a, it's, you know, it's a solid, as you would call it a solid, right? But what happens then is you increase the temperature, there's enough thermal energy to overcome these secondary bonds. So that now, if I pull on it, I'm just sliding these past each other. I'm not having to overcome these bonds. Right? I'm not having to break those bonds mechanically because they're already broken thermally. So the modulus drops significantly because it takes less force.
It's really frustrating.
When I was a kid, we used to make Christmas ornaments out of plastic cups. So you take a plastic cup and stick it in the oven, like just a clear plastic cup. Stick it in the oven and let it collapse on itself, and they would all sort of randomly form some random goo or whatever, and it would all just sort of collapse down into this puddly thing. And then you take it out, and it's this viscous thing. You can poke a hole through it very easily, and then you let it cool, and you hang it on the tree. It's just kind of cool.
And carcinogens get in your oven.
No. We use carcinogen-free. We use carcinogen-free polymers. Anyway, so that's what this is. This is it turns into goo and it runs. So it's viscous. Okay. Does that make sense? Okay. For elastomers, things like rubber, like a rubber band, room temperature is right there in the middle. That's why rubber bands behave like rubber bands, because room temperature is enough to overcome the secondary bonds and make it rubbery. If I take that rubber band, put it in liquid nitrogen, it becomes rigid.
Less TG.
That's why I said it's the glass transition temperature in ceramics, but I can't remember if it's.
Okay, so the G stands for glass.
Yeah, I think. Let's see here. T sub G. The glass transition. Yeah, it is. It is. Okay, I just didn't know the glass transition. The same term was used for polymers. Yes, it's the glass transition temperature.
So when you do glass blowing, where do you bring it to?
So glass blowing, we want to be. So in glass blowing, you want to be somewhere north of TG. But it's a matter of staying around here, because if you get too far out there, then it falls apart, right? So we're going to be in this range between the melting temperature and the glass transition temperature. Okay. What else do we have?
Experiment.
Yeah, we should do demonstrations.
Yeah, I know. There's a lot of things we should do in this class that I don't do because I didn't have time to prepare. But now if I make my polymer crystalline, so this is for just like an ordinary amorphous non-crystalline structure. I can't remember, did I talk about polymer crystals? How they're shaped? I can't remember if I talked about polymer crystals. All right, never mind. I'll have to come back and talk to you about the okay. Polymers, typically the way that polymer crystals are formed is to take the long chain and wrap it back and forth on itself. And I'm trying to draw it in 3 dimensions here.
Sea sturgeons?
You kind of see what I'm talking about there? And it kind of stacks itself like
Can
that.
you like try and draw it from the right side?
Is that still supposed to be just one, or is that multiple?
This is a single crystal. This is a chunk
So is that like
of a single crystal of polymer.
wavy?
Can you see what it is?
Wavy.
Seriously, can you
Yes.
see what it is?
Yeah.
Okay. So that's the way how polymers become crystalline. And if a polymer is crystalline, then that structure, depending on how crystalline it is, may destroy this completely. Okay, so you don't ever get this kind of leathery, rubbery behavior if it's crystalline to begin with, because there's so much of that. There's so many of those secondary forces all in this nice organized package. And if it's partially crystalline, you get something in between. depending on how crystalline it is. So this is crystalline, and this is amorphous. The non-crystalline. Yes?
Is that like a natural process, or is that?
Crystalline polymers, yeah, they're really hard, that's hard to make, it's not really natural. I mean, I suppose it could be a natural process and occurring over a long period of time, but it's hard to make polymers crystalline. It's very difficult to get them to organize that.
So each cell is its own molecule.
Essentially, yeah. I mean, each grain is its own molecule. It would actually be the way I would do it and talk about it. That's not a single crystal, that's not a single unit cell. The unit cell structure doesn't really apply.
Yeah.
Okay. So, and when you're in that rubbery region, if I stretch the polymer, if I actually do a stress strain kind of curve, let's do it this way, right? The elastic region of the polymer usually will do something like this. I stretch a rubber band. So I pull on a rubber band. If I pull it a little bit, it doesn't take much load, right? If I were just modeling it as according to Hooke's law, this would be a straight line. F equals kx, right? But in fact, with a polymer, you get this straight line behavior down here, but then it stiffens up. The modulus increases as I apply more load in a nonlinear fashion. Because down here, I'm just overcoming these secondary bonds. Up here now, I'm stretching the primary bond. Right, so it's easy to stretch the secondary bonds, but once you've got the secondary bonds stretched, then you got to stretch the primary bonds, and it takes more. It's a stiffer material. Okay. And what's more, if I release it and come back, and that's the way up, this is the way down, there's hysteresis. It doesn't come down the same way. There's actually energy lost in between. Because as I pull, that's not why they get less stretching now. What happens is, when I pull it, those secondary bonds break, right? Breaking, and they release heat. So when I pull on a rubber band, it gets hot. I've talked about bringing rubber bands in, I keep forgetting because nobody reminds me. You pull on a rubber band, put it between your lips, and you pull on it fast, and it gets hot.
Figure it out.
My lips are gonna taste like rubber now. Gross flavor.
Okay, you're on your own for that. Anyway, you pull it fast. You pull it fast, and you'll pull on it, and you'll feel the heat release. And then when it releases, it actually feels cold because energy is going back, thermal energy is going back in to recreate those secondary bonds.
It picks up thermal energy
From its environment when it releases. Yeah, so I pull the rubber band, it gets hot, that heat's released to the environment. When I shrink it, it feels cold, it'll feel cold on my lips because it's extracting heat from my body to recreate those secondary bonds. No. Exactly. You guys are just full of these, you in particular are full of stupid questions.
Those are joke questions.
I don't know, this is not a joke question.
Did you almost say it was an
It's not appropriate for this time. Okay.
Where do you get off?
Already did that, past that. Okay. And in fact, if I have a non-elastomeric material, if I'm up here in the rigid region, this curve instead looks something like this. There's actually a linear region first before it does that. Okay, so this is in this region here, right? This is breaking secondary bonds. Right, that's what that second region is, breaking the secondary bonds. So it takes very little energy and it's kind of has a low modulus, right? But in a rigid, if it's a rigid material versus an elastomer, right? Yes?
I have a question. It kind of goes back to the log of the modulus of elasticity. Is there just one modulus of elasticity? Because if it's the slope of that It's the slope of the more or less linear part of the stress strain.
Right,
Is
right,
that
so
correct?
what we're talking about here is we're picking a particular point in that graph.
Okay.
So this may be the initial, right? So the rigid one's gonna have a higher modulus at the initial point than does the elastomer, which is already out here in this lower modulus region. Does that make sense?
Yeah.
Okay, so we're just taking that initial slope before we get into secondary stuff, other stuff. But with a rigid polymer, it means we don't have as much thermal energy, right? For a rigid polymer, it means our room temperature is down here, right? It's below TG. It's not enough to energize those secondary bonds. And so this section here for a rigid polymer is stretching the secondary bonds. So with a rigid polymer, we have to first stretch those bonds, then we can break them. Breaking them is a low modulus, because once they're stretched, then it only takes a little bit more energy to break them. But because we don't have the thermal excitation to get us into that elastomeric region right from the beginning, we have to mechanically stretch the bonds first. So a rigid polymer will behave like that. An elastomer, where room temperature puts us into the middle of the temperature range, behaves more like this. Essentially what happens is, with an elastomer, the thermal energy has moved us over this section. We've overcome this initial section thermally instead of mechanically.
So you can get more or less the same effect, but you just have to do the mechanical part first for
Right.
rigid, and
Right.
then eventually it will act
Right.
like.
Right, the elastomer does. Right, so, trying to think if you've ever experienced where you might have experienced that. So, yeah, I mean, it happened like I'm thinking of an old, like a Pepsi bottle, you know, or a soda bottle, you know, the clear plastic, whatever that is, polyethylene, whatever the clear plastic, #1. Take one of those, you take a chunk of that material, it will kind of behave like this. It'll be hard to stretch, but then at some point I get it to the point where, and it actually stretches a little bit easier. I mean, again, still, it takes more load,
Yeah.
right? So it's still taking more load. It's not like it's easier to stretch, it's just I get more deformation for every increment of load that I add. And then it becomes really rigid, because up here, once I've broken all the secondary bonds, now I'm stretching the primary bonds. And those are tough to stretch.
Once you stretch the primary bonds to the point where they break, that's when the thing itself breaks, right?
And then that will be here.
So it's not like an organized, there's not a bunch of chains in a line, they're kind of just all like in a mesh, like tangled up together?
Right, typically. Now, sometimes they are changed to line, depending on how it's been manufactured. If it's a line, then you get very little of the secondary bond breaking stuff. You can move more quickly into the stretching the primary bonds.
You don't just shear off the secondary bonds, you can actually like.
So if I have a line, if I align my polymer backbone, I just want to make sure I'm not going to run out of time. Hold on, let me make sure. Yeah, okay, we're good. If I align my polymer chains in the manufacturing process somehow, then when I go to pull on it, there's only a little bit of alignment left, right? I mean, you can't get them exactly perfectly aligned.
Right.
So they're going to be a little wobbly, but they're all going to be kind of like this, right? So I'm going to have a series of polymer chains that look like this, right? If I manufacture them, and there might be a little bit of, you know, hysteresis in there or something like that. Okay. So if I have something like that, I pull on it, there's still room to straighten break some secondary bonds and straighten out those primaries, but it's going to be very little. So I'm going to get if it's a rigid polymer like that, I'm going to get very little of this before I quickly move right into stretching the primary bonds.
And if you're gonna stretch it the other way, then it'd only be secondary bonds until they totally break, or mostly.
Yeah, I'm not sure if that's the case actually. Because if I pull this sideways, it's going to want to neck in so that these things are going to want to kind of do this, right? If I'm pulling on it, they're going to want to do that. If I grab over the center and pull on it. So I'm eventually going to also have some primary bond strength. But it's not as strong as it would be with aluminum. So polymers that are rolled out in sheets oftentimes have different mechanical properties in the two directions. Because in one direction, the chains are kind of aligned the way it was rolled, the other direction, not so much. Okay. See if I've left anything else. The other thing about polymers is they can be very susceptible to humidity. Because water, they're not inert. Unlike the ceramics and even to a lesser extent metals, which are somewhat relatively inert in at least normal atmosphere, they'll rust, but they'll corrode. But polymers are much more active with their environment, so they'll humidity and temperature have a much bigger effect on polymers. UV degradation, right? You guys are familiar with that. And so there's all kinds of ways that we can get polymers to degrade. We'll talk a little bit more about kind of the ceramic stuff. Fracture mechanics, yeah, okay. I think that's probably as much as I want to talk about. There's a little bit more about viscous deformation of glasses that occurs at high temperature. We'll come back and talk about that later. That's fine. That's fine. Okay, so anybody have any questions?
This is kind of the future. What will a test in this class look like?
So it is very much like any of my other classes. There'll be, there'll probably be more problems because a lot of them are much more sort of knowledge-y. They're not calculation kind of problems. They're not analytical problems as much as they are, being able to apply an understanding of the concepts. And so it might be 8 questions on a test instead of 4 or 5. But still, that's still the general idea. Some of them might be, I might give you some crystal structure stuff, and you've got to identify characteristics of the crystal structure. I can see asking, where are the locations of the octahedral interstitial sites in this lattice? And you have to tell me what they are.
Threw up in my mouth a little bit.
Can you say that again? Octahedral
Interstitial sites.
sites.
Did we ever learn that?
You've learned that, yes, you have learned that. Right? You remember the tetrahedral interstitial sites?
I think we'll be sick.
So in an FCC lattice, what are the octahedral interstitial sites?
I know BCC.
Is that? 1 half, 1 half, 1 half is one of them. The body center is an octahedral interstitial site. So,
And then all the corners?
And then quarter.
no, quarter is still tetrahedral.
The faces? That's what the body center faces.
Hold on, let me draw the whole thing out. And then we got,
This is FCC, right?
Faces.
Can we also put PowerPoints on Moodle?
I can, for a fee. I will put the PowerPoint, yes. Okay, so that's the FCC. Everybody see that? She's done a very good job drawing that one. That's a little more. Anyway, so the octahedral interstitial site is the center of the cube, which connects that octahedron from everybody kind of see how that little diamond shape is in there? 2 4-sided pyramids on, sandwiched together. So that's an octahedron. The center of that octahedron is an octahedral interstitial site. Interstitial.
1 half, 1 half.
1 half, 1 half, 1 half. Right. But that's not the only one. There's also an octahedral interstitial site here. Let me draw that one in there. There's also one here at the edge. Because I should draw that in a different color. You guys can come to me for pulling this while I do it, because it's on the screen. All right, let me get the blue. So this one has an octahedron around it, and then going over to the face center of the next crystal, and then going down to the face center below it.
There's one of those on each page.
And so it makes an octahedral so that it forms an octahedron?
Right, there's an octahedron of other atoms, the nearest neighbor atoms.
But they're not other interstitial atoms.
Right.
What do?
And just like the tetrahedral sites, I'm going to draw more on this diagram and make it even worse. The tetrahedral interstitial sites now are between here and here and here. That's a tetrahedron. See, that's an inverted three-sided pyramid.
So, but then,
So the center of that at a quarter, or the equivalent,
But that wouldn't be in an FCC, would it?
yes.
Do they both exist in an FCC?
There's an octahedral there's a tetrahedral and an octahedral.
So there's also
both
then,
in FCC.
then there's also an
Octahedral.
so there's, but there's not a tetrahedral inside of an octahedral.
No, they are different.
So what's the center of that, like 1/2, 1/4, 3/4?
Well, it depends on where your origin is. This one, there's one, if you go in the back quarter, there's a quarter. So you go a quarter, and a quarter. Basically, a quarter of the way through the body diagonal is where that is. So if I go start here, and I work my way to there's the body center, that's halfway through. A quarter of the way through is a tetrahedral interstitial site.
so where's it's tetra, that's 4. So it's 4-sided.
4-sided, 4 equal triangles. 4 equilateral triangles.
Goes to that corner.
This 3, those 3.
I can hard time seeing how the center of that is a quarter.
Yeah, that's why you don't use my drawings and you'll be the ones in the book.
So so like the tetrahedral one, it uses 3 faces in one corner. Like
It
3
uses-
face atoms in one corner, right?
Yeah, you're right, that's right, you're right, I didn't draw
I
that
think
well.
you'd use
You're right, you're right.
2 bodies and 2 faces.
You're right,
You drew like part of another octahedron.
right, you're right. Anyway, yes. It uses these 2 faces, and anyway. I've mucked my darling up so far, I can't even tell what I've got up there. That's why I say, I refer to your book.
And an interstitial site is just like another atom.
An impurity
that
atom,
exists
instead
in a
of
part
small
of itself.
So those are the kinds of things, those are the kinds of questions I might ask. Identify the octahedral interstitial sites in an FCC lab.
Would there be any practice exams?
I have no practice exam.
You would already do the question on yourself before they Well, I didn't know all the questions.
No, very well. There are short answer, yes.